friends, welcome to our world. This is the 101st episode in a science series. So today in science, it is chemistry. And today we are going to talk about an important topic in atoms and molecules. In chemistry, that is atomicity. Let's begin. So let's begin with one important topic, types of molecules. So, molecules. There are two main types of molecules, and this video is dedicated to one type of molecule. That means atomicity is in that specific type of molecule with me. So one is heteroatomic or heterogeneous, and then is the homoatomic or homogeneous atomic molecule. Okay. So there's a difference between both of these types of molecules. In heteromolecules, there are different types of atoms in it. For example, hydroxide as an example. There are two different types of atoms. It is O and H. They are not the same. Oxygen and hydrogen are of course not the same atoms. Meanwhile, there are homoatomic atoms such as H2O. No, H2. Just H2. See, both of them are hydrogen. They are the same type of atom. So this counts as a homogeneous homogeneous molecule, while this is counted as a heterogeneous molecule. And today's video, which is about atomicity, is inside homogeneous molecules. Yeah, that means it only accounts for homogeneous molecules, not for others. Okay, let's just quickly wipe the board. So, take hydrogen, H. So, hydrogen cannot normally exist on its own because it will want to quickly react. That means in a way it can exist on its own, but it's not the most stable in that way. So, it just wants to react with something else, whether it is itself or something else. And this is the most stable form of a hydrogen. This is a hydrogen molecule. A hydrogen homogeneous molecule. So this has two hydrogen atoms. So this completes the outer shell for both of these atoms. We discussed about this covalent bond like a year or so ago. It's been like 50 or more weeks ago in chemistry. But let's continue. So this covalent bond will make them both very stable. Yeah. So this makes a H2 molecule, which makes hydrogen's atomicity 2. So an atomicity is just the not just minimum, the number of atoms in an atom's molecule, an atom's homogeneous molecule. So for hydrogen, there is H2. And this is not always the same number. For a few atoms, there is not just one but many other different atomicities. And so, let's begin. So there are also other elements with varying atomicities such as oxygen. So this is the normal O2 which we breathe and it is in the air. But there is another form of oxygen. It is in the sky and I'll give a hint. It's O3 or also known as ozone. So in this version of oxygen, it has an atomicity of 2, and in this version of oxygen, it has an atomicity of 3. So oxygen could be said of having both 2 and 3 atomicities. Yeah, this is practically what atomicity is. But how to find out the atomicity of a molecule? An atom, an element. Okay. Let's find out. There's no exact way how we can find out the atomicity of an element. We just need to do some trial and error stuff like that. Like, how should I say it? Like check each of them. Every molecule, every homogeneous molecule of that element. We should check. Oh, this element can be split in like this. This molecule is made out of 2 of the same element. We can check like that. Because there's no other option. We can't find the atomicity of elements without doing that. There's no other chemical calculations which we can do. Except of course there are a few rules. First is metals. You know metals. Those things which or which make up most of the periodic table. They take a big chunk of the periodic table. So most of these metals have an atomicity of 1. Why, you may ask? Because while other non-metals and sometimes metals and non-metals have covalent and ionic bonds which need valency to work, but which need atomicity and valency. Valency is another topic which we will discuss later. It's much more complex. Yeah. So metals make up metallic bonds. They're not exactly connected. They do not share the atom electrons directly, but it is like a sea where electrons just casually roam around wherever they like. So this roaming around of electrons will cause a bond together, and so there's not exactly a molecule in this. It's just atoms being pulled together, but not to be a molecule, to be a specific structure, an element. So this pretty much every metal has an atomicity of 1. Along with these metals are noble gases. Noble gases cannot mix with any other stuff, not even with themselves. Such a few examples are helium. Wait, I'm using black marker. Such as helium, xenon, argon, neon. So these are a few examples of noble gases. So they can't do any bonds. No metallic bonds, no covalent bonds, not even ionic bonds. So they just stay together. They do not have a specific molecule. It's just like the metals, but for a different reason. So they all have an atomicity of a single 1. Yeah, let's just continue. So there's also a small way of how we can, that means there's a small trend in the periodic table. The 14th and 16th rows are the oxygen group and the nitrogen group and the oxygen group. This is the 15th, by the way, sorry. The 15th and 16th groups of the periodic table, the columns that is, most of them actually have, guess it? Most of the elements in these rows have either 2 or polyatomic, or diatomic or polyatomic. Yeah. So, okay. And there's one more topic I need to cover. That is one important element which defies all rules of atomicity. This is the one and only C or carbon. Let's take another one. Yeah, okay. So carbon makes up, so it is very strong together. It will make up so many bonds with each other to form a humongous molecule. For an example is diamond. It is just a big structure of continuous atoms of carbon being bonded together. They do not have an end. They are completely bonded together by covalent bonds, which makes it a big, humongous molecule. But we shouldn't count these structures. Atomicity shouldn't be counted for such big, humongous structures because they're just too big. We can't exactly define how many atoms there are in like this much diamond or this much graphite. We can't exactly define them, but we can define a few molecules, and carbon has a very high atomicity at that. So there are a series of molecules which carbon makes up known as fullerenes. These are basically shapes, three-dimensional cages. Like they can hold together smaller atoms inside of them. So these cages are known as fullerenes. So the smallest fullerene molecule is just 20 atoms. Yeah, just 20 atoms. 20 carbon atoms that is. And these are completely homogeneous, made out of carbon. While the largest, a very large one, has 540 carbon atoms. Now that's a lot of atoms. We can define the atomicity of carbon as either 20, as either 60, there are different fullerenes as well, or even 540. But there's one thing, carbon nanotubes. They could also be counted as molecules, but because they are like polymers, because they're just a continuous line of the same thing. but we shouldn't count them again because they could go on forever. Just like diamond or graphite, they have an uncountable amount of atoms in them. That means an infinite amount. So we shouldn't count them. They're structures again, not molecules. So yeah, this is for today about Atomicity, and of course I need to buy new markers. So bye.